Series with you all. So for those of you who do not know, Astronomy on Tap is actually an international organization of local public science talks that are taking place in pubs, bars, breweries all over the world. And so if you don't actually live in Orlando, you can actually check out astronomyontap.org, and I'm sure that you could find one in a city near you. But tonight, for our launch event, we have two wonderful speakers who will be presenting talks to you all. In between those two speakers, we will be having a 20-minute intermission during which we will be having space trivia with a chance to win some fantastic prizes that are up on this front table here. Along with that, we have some stickers and patches and some other free stuff for any of you guys to take on this front table as well. So as this is our first event and we are still an up-and-coming series, any donations that you would like to make would be greatly appreciated. We have a jar up front for any cash donations you'd like to make, as well as a Cashapp, which is AoTOrlando. And so following tonight's event, we would also love if you could fill out our feedback survey, which you can access via the QR codes that are on your table. So if you could fill those out, let us know how we did. We'd really appreciate it. And I think that might be all of our... Oh, for those who might not know, there is a launch tonight from Kennedy Space Center. There we go. So the launch of the Artemis 1 mission is going to be launching around 1:04 a.m., is that right? Yeah, 1:04 a.m. from Kennedy Space Center. It is the largest rocket that has ever been launched, so you all should definitely try to see it if you can. And with that, I think it's time to introduce our first speaker of the night. So we have Dr. Phil Metzger from the Florida Space Institute, who will be giving us a talk on, is Pluto a planet and does it really matter? So let me pull up his slides. And take it away, Dr. Metzger.
All right, thank you. All right, thank you. This is cool. Astronomy on Tap. What an awesome idea. Okay, so I'm going to talk tonight about Pluto. And does it really matter if it's a planet or not? I often hear people say, Pluto doesn't care if we call it a planet. That's kind of missing the point, and I'm going to explain why. Okay, let's see. This is not working.
Turn it on the side.
Somebody want to give me a hand with this? I guess I can do this. I'll just do that. All right. So, so this is the roadmap of where we'll be going with this talk. Taxonomical concepts like planet evolve to match whatever theory we're working on. And I'm going to provide evidence. This is based on a paper we just got published in Icarus, which is a planetary science journal. It was peer-reviewed. It represented 5 hard years of research. We read essentially everything in astronomy from Galileo to the present, and reviewed how the concept of a planet has evolved over time. So we're going to make the case that planetary scientists work on theories of planet formation and life in the cosmos arriving on planets. And so that type of theory drives the concept of a planet. On the other hand, I want to show you that culture has been interested in astrology and theological meanings of planets. How do planets tell us about ourselves? And it's kind of human-centric. And this leads to a different concept of what a planet is. In both cases, taxonomy is functioning properly because it's evolving to match the theory we're trying to discuss. But I'm going to make the case that this was the ultimate cause of the split in the planet definition in 2006, when the non-planetary astronomers unwittingly adopted the cultural view because they wanted to be sensitive to culture. and therefore adopted a concept of a planet that comes from astrology and really has no scientific value. Whereas planetary scientists tend to favor a geophysical planet concept because that's the one that came from Galileo and Copernicus and Kepler and has evolved over hundreds of years to be useful. Okay, so that's where we're going on this. So we'll start way back, 2,200 years ago, in the Hellenistic pre-Roman period. This was a machine that they had made to track the motions of the things in the sky. It's Anacathera device, I think. I don't know how to say it. I'm getting a thumbs up back there. Okay, so this device tracked the motion of the heavens. It was a geocentric idea of the solar system, but it represents this view that the heavens are mechanistic and orderly and repeatable. When we switched to heliocentrism, the machines that we built looked a little different. This is an orrery. It represents the sun and the major planets with the secondary planets or satellites orbiting around them. And again, it's very orderly, mechanistic, very predictable, and it's clean. There's no small bodies, there's no asteroids, because those weren't known at the time. But then our concept of the solar system got challenged. Planetary scientists and lunar scientists especially started hypothesizing that these craters, like this, but on the moon, were not volcanic calderas, but instead were impact craters. And that was kind of shocking because that implied there's a bunch of stuff flying around in the solar system that we never knew about before. And of course, now we know that the solar system is packed full of millions and really, if you go all the way to dust-sized particles, trillions or quadrillions of particles, all the way from the size of Manhattan down to dust specks. And they're mostly surviving over a long time in this main belt, the main asteroid belt between Mars and Jupiter. But you see there's these Trojan populations, the Hildas, and in the inner solar system there are asteroids as well. They're everywhere. But then in 1943, Kenneth Edgeworth, the astronomer, proposed that there might be something like that to explain where the comets are coming from. And then in 1951, Gerard Kuiper said, yeah, it probably did once exist, but it's been cleared away by now. Well, that's only partially correct. We call this the Edgeworth-Kuiper belt, or more commonly just the Kuiper belt. And now we've measured many of these objects. We know that they exist, and they're roughly located at 30 astronomical units from the sun, which is, an astronomical unit is the distance from the Earth to the sun. So 30 AU, so just outside the orbit of Neptune, out to about 55 astronomical units. And the Kuiper, we think the Kuiper belt is, well, it's a disc-shaped belt. We think it's just a tiny little piece of a much larger cloud, that's a spherical cloud that we haven't measured yet, we call the Oort cloud. So this is a messy view of the solar system, different than the one that our ancestors believed and taught when they created astrology and all these hypotheses about the orderliness of the cosmos influencing the life, the events on the Earth. Well, the first object in the Kuiper belt was discovered before we even hypothesized that there was a Kuiper belt. And that was Pluto. In 1930, it was found by Clyde Tombaugh. And it is the largest Kuiper belt object in terms of diameter, slightly larger than Eris, although Eris might be a little heavier. But it's also on the inner edge of the Kuiper belt. So it's large, it's close, and that's why we could see it first. Now, a few facts about Pluto. It's a whole system. There's 5 moons around Pluto. And the largest of those moons, Charon, is large enough to be considered a dwarf planet in its own right. Because it's large, it's gravitationally rounded. It and Pluto are tidally locked, always facing the same way towards each other, swinging around like 2 ice skaters. So people often call it a double planet or a double dwarf planet. Now, some people have said Pluto is just a big comet because it's a dirty ice ball. Well, that's not true. It's only about 30% ice. It's about 70% rock. And even if you stripped off all the ice, the amount of rock that there is large enough to be a dwarf planet. So it's definitely not just a comet. just to get that out of the way. And for what it's worth, I just threw this in for grins. Now, when we measure the size of Jupiter, we're measuring to the top of the atmosphere, right? Because it's mostly gas. When we measure Saturn and Uranus and Neptune, we do the same. Now, why don't we do that for Pluto? If we measure to the top of the atmosphere of Pluto and the top of the atmosphere of the Earth, Pluto would actually be larger than the Earth because it has such a gigantic atmosphere, although it's extremely thin. So whatever, just thought that's an interesting fact. But when the New Horizons spacecraft flew past Pluto, after it got past it, it spun around and it looked back at Pluto, where Pluto was backlit by the sun, to get a look at this atmosphere, and we saw that it's a layered atmosphere. It's got layers upon layers, and we know it's complex. There's circulation in the atmosphere. There's climate changes over its orbit around the sun, so it's very complicated. Some beautiful pictures of Pluto, the mountains. These mountains are made of water, but it's harder than granite at that distance from the sun. These mountains are as large as the Rocky Mountains, and they are currently building. There is mountain building still going on Pluto. The snakeskin terrain, which is a very bizarre terrain, draped with organic molecules, which are the building blocks of life. I've already mentioned the size of these mountains. Off to the right of the mountains are nitrogen plains of ice. So these ice plains and then the mountains. But I want, these ice plains have flowing glaciers flowing down out of the mountains. We see the ice flowing down and spreading out as plumes. So there's active glaciology happening on Pluto. On the ice plains, there are different plates, and at the crevices of the plates, some ice mountains apparently have formed. And Alan Stern, the head of the Pluto mission, said that that looks like anybody want to guess what he said it looks like? Something from Star Trek. A Vulcan bird of prey, is that what it's called? Vulcan spaceship? No, Klingon. Klingon bird of prey, yeah. Okay, so I'm going to zoom in. Here's the ice plains. There's the bird of prey. I'm going to zoom in right up in that part of the mountains. This is an ice lake up in the mountains. But what is this around the ice lake? It looks like a paleo shoreline where the level of the lake has gone down over time. So maybe it goes up and down as Pluto goes around the sun. I don't know. But the point is, it's a complicated world. And out on those ice plains, there are these pits, sublimation pits. They're about the same diameter as the length of a football field. And the funny thing is, these sublimation pits where the ice is subliming and leaving a hole in the ice, they're all the same size and they're lined up. Some of them are elongated, but they're all in a line with each other. So what organized the sublimation process to line up like that? Well, here's a clue from Earth. The clouds. Look how the clouds, they're all the same width and they're lined up. We know that this happens because of circulation, rolling circulation in the atmosphere, so that you get phase change, condensation of water along these long linear features. So maybe on Pluto, there are circulation cells rolling in the ice and under the ice, in the water that's under the ice, causing these complex phase change phenomena to be aligned like this. So this is just more evidence about the dynamic nature of Pluto. Now, Pluto is not the only Kuiper Belt object that is a dwarf planet. The International Astronomical Union has labeled 4 of them as dwarf planets. For reference, there's Earth's moon, and this is a dwarf planet that's in the asteroid belt series. So only 4 have been formally identified as dwarf planets, but we know there are about 150 to 450 planet-sized objects in the Kuiper Belt. The reason they have not officially been declared dwarf planets is because they're so far away you can't verify their size, but we know by statistics that about 150 to 450 of them are planet-sized. So there's a lot of planet-sized objects in our solar system. This is Charon. As I said, it could be a dwarf planet, and I don't know why it hasn't already been acknowledged that it is one. Now, the IAU, the International Astronomical Union, when they voted and said that Pluto is not a planet, they also defined dwarf planets. And they said a dwarf planet is an object that orbits the sun it's large enough to be rounded by its own gravity like Pluto, and it has not cleared its orbital neighborhood. This is the controversial part. Now everybody agrees it's fine to call Pluto a dwarf planet. The issue is, are dwarf planets a type of planet? And our argument is that if they're not, then it renders the word planet into a non-useful status. There's nothing that you can say about that class of objects that as a class, if that's how you define it, other than they clear their orbit. But nobody is publishing any papers about the nature of planets or what they do or how they do, based on clearing orbits. There are no published papers talking about planets as defined by the IAU, but there's hundreds of papers and conference presentations using the geophysical definition, violating the IAU even after the IAU voted. Okay, but we think that a planet is defined only by this one thing: large enough to be rounded by its own gravity. If it gets kicked out of orbit and becomes a rogue planet, it's still a planet. If it gets captured into orbit around Neptune, like Triton was, it's still a planet. If it formed around another planet, like Europa or Titan, but if they're large enough to be a planet, they're still planets. That's why we say Titan has a planetary crust, a planetary core. It doesn't have a satellite crust, it has a planetary crust. And I'm going to show you historically why it developed this way. Now, gravitational rounding, it's not an arbitrary definition. So this is Arrokoth, which is a Kuiper belt object that the New Horizons spacecraft flew past, got this amazing picture of it up close. It's a small, lumpy object, not gravitationally rounded. There's no active geology, no lakes, no glaciers. There's no reprocessing of minerals. There's no organic activity happening. There's no mantle plumes. There's no volcanoes. It's just a dead rock. But Pluto, because it's gravitationally rounded, something turns on at that size in an object. You get melting of the core, melting of the mantle, you get mantle plumes, you got transport of energy, you have reprocessing of the minerals, you have mineral formation, you have outgassing, forming lakes and rivers and atmospheres, and you have volcanism and mountain building, and then you have all the fluid dynamics, and it becomes an active, complex world, and that all seems to turn on at the point of gravitational rounding. So our argument is that's the important thing, and it's really a different class of object than this, regardless what orbit it happens to be in. And part of the reason this is important is because orbits don't stay the same. Planets change their orbits. This is a model it's called the Nice model. And this is a map of Jupiter, Saturn, Neptune, Uranus. These are swapped because in about 50% of the models, Neptune and Uranus swapped orbits with each other. And this is what the model looks like. Jupiter and Saturn got in resonance. It kicked Saturn. Saturn kicked Neptune. Neptune flew out past Uranus, plunged in the Kuiper belt, scattered most of the Kuiper belt, leaving a much smaller Kuiper belt, and that caused about 10% of the Kuiper belt objects to bombard the inner solar system, which is where we think the water and the carbon that forms our bodies came from. So you're made out of Kuiper belt objects, we think. So this was really important in the history of our solar system. It's still a theory. I think it's a pretty strong theory. I'm not sure. Do you think it's a good theory, or? Okay, so anyways, this is the Nice model. But the point I want to make here is, and by the way, this explains a lot of the weird dynamical features of the Kuiper belt. The point I want to make is orbits change, okay? So it's like some mammals evolved back into the ocean. We didn't say they're now fish. You know, dolphins didn't become fish when they evolved back into the ocean. They're still mammals. They're marine mammals, so we have a subclassification of the mammals. So their current environment may change over time, but the essence of what they are is defined by intrinsic characteristics. So this is the untrue story we've all been told. This is in every astronomy textbook. We published a rebuttal to this in this long Icarus paper. What we were told is that in 1543, Copernicus published a book which eventually convinced people to give up geocentrism, and because of that, moons became non-planets. So the sun was no longer a planet, the moon was no longer a planet, but the Earth became a planet. That's what they always say. Then in the 1800s, we unwittingly accepted a few asteroids as planets until we got up to about 15 of them. And then we said, oh, that was a mistake. There's too many of them in the same orbit. Obviously, they're not planets. And so we started numbering the asteroids, and that signaled the point that we didn't really believe they were planets anymore. And so the number of planets went back down again. And it's been that ever since the mid-1800s. We realized swarms of objects are not planets. To be a planet, it has to not be in a swarm. It has to clear its orbit. And that's why in 2006, the IAU voted to say that the Kuiper Belt objects that are large as planets are not planets. Okay, that is not a true history. So there's other symptoms that there's a major problem happening. The arguments given for that vote were not scientific arguments. One of the main arguments that was given at that assembly was that we need to create a definition of a planet that keeps the number of planets small so that school children can memorize them. I'm not making this up. That was literally one of the main arguments that was being circulated at the assembly. Furthermore, another symptom that something bad was going on was the IAU broke its bylaws in order to have this vote because they knew there was no consensus, and the bylaws were written to prevent them from doing things when there was no consensus. But they really wanted to define what a planet was, and they knew the only way to get it done was to keep the vote secret. And so the bylaws say you have to let everybody know, put it on the website 6 months ahead of time so that everybody can review it and come to the convention ready to make your arguments. Well, they did not let anybody know there was going to be a vote. On the second day of the assembly, they announced it. Everybody was pissed, and they voted down what was proposed, and in 3 days, they came up with a different proposal. Nobody had a chance to review it. Nobody had a chance to buy tickets to fly to Prague to make their case, and it was pushed through. Why would they break their bylaws to do this? Okay, that's a symptom that something non-scientific was going on. Furthermore, planetary scientists to this day are not using the IAU definition in any pragmatic science. There is no theory of nature that you could discuss which only includes the bodies that are rounded by gravity and clear their orbit and directly orbit a star as a category. And we are using a different definition in pragmatic science. And furthermore, there was a lot of people claiming that the concept of a planet isn't even a science issue. It's only a cultural issue. And some astronomers were saying the concept of planet isn't even useful in science, so it doesn't matter. Just go with the cultural definition. Well, mammal is defined by science. Gene and feldspar are defined by scientists. What's different about planet? Mike Brown wrote in 2008, "This debate is purely cultural." By the way, Mike Brown calls himself Planet Killer on Twitter. He wrote a book called How I Killed Pluto and Why It Had It Coming. He was the discoverer of Eris. But he said, "This debate is purely cultural. Claiming that there are scientific reasons to define planet should disqualify you from further discussions on the ground that you are conflating the job of science and the job of culture." Okay, so in ancient times, planets were considered to be stars. All the stars moved. The fixed stars were fixed relative to each other, and they moved together around the sky, whereas 7 of the stars, the sun, the moon, and the other 5, moved at different speeds. And so they were called the wandering stars because they weren't fixed with the other ones. The word wandering in Greek is where the word planet comes from. The Greeks knew that Jupiter was bigger than the moon, but it was just farther away. So they weren't thrown off by the fact that the sun and the moon looked bigger in the sky. So there were 7, and culture developed to be very powerfully related to this. They believe that planets have a purpose. They believe that they're intelligent beings or they have souls. That sounds kind of strange, but even Kepler believed the sun has a soul as the explanation for why it puts out light. I've read his books, and he said the sun has a soul. But the Bishop of Paris condemned the idea that the planets have souls in, I think, the 12 or 1300s. So even till pretty late, they believed planets had souls, and that's why they're named after gods, because they thought they were gods. because they believed their purpose was to influence the Earth. This influence might be quantifiable, so cultures all over the world, the Mayans, Indians, everywhere you go in the world, Druids in England, they all developed astrological systems, and they studied the motions of the sky to try to figure out how the planets were influencing us. But Galileo, it was really Galileo, not Copernicus, who changed the concept of a planet. He used his telescope and looked at the moon and discovered that the moon is a geological body like the Earth because it has mountains. And this implies that the moon undergoes change like the Earth does. So it's not governed by unchanging physics, it's governed by earthly physics. Earthly physics and heavenly physics are united. Therefore, the Earth is in the heavens along with the moon. Therefore, the Earth moves. He also could see the Earth shine on the moon, and he argued this. The Earth is a star as well, a wandering star, because the Earth gives off light just like the other planets. He also argued that the moons are planets. So about the 4 moons of Jupiter, he said, the occasion of discovering and observing 4 planets never seen from the very beginning of the world up to our time. He called them planets. And it was important that the moon was a planet because he was trying to compare the one planet that we can see really well, the moon, with the Earth to argue that the Earth is a planet. There was no motive to say the moon is not a planet. That would have undermined his argument. And all scientists said that moons are planets. So we've got hundreds and hundreds of quotes. They're on my website. And if you want to get our paper, we've put it all on the website where it's all downloadable. And we also gave it as supplementary material to the journal. But Jupiter has 4 such planets. A planet was not defined by its orbit, even after the Copernican revolution. So I'm not going to go over all of these, but talking about the moons and the primaries, true planets, all of these are, whatever be their distinguishing names, whether they're primary planets or secondary planets, which means moons. Their distinguishing name, primary or secondary, doesn't matter. True planets, all of these are. And then he gives the definition of a planet. 4, they are solidified bodies shining by reflected light. That was literally the definition that Galileo created. And even as late as 1910, that was still the definition of a planet. Had nothing to do with orbits. Okay, so we believed planets were worlds. They still believe that the planets must have been created for a specific purpose. Since they don't orbit the Earth, their purpose is not to influence the Earth. What is their purpose? And everybody, maybe not Galileo, but just about everybody else concluded that they must all be homes of civilizations. But I'm going to skip down to, this is all on our website, but Brewster and Whewell debated in the mid-1800s. It was a debate just before the debate over the origin of the species. A theologian and a scientist debated about whether all the planets have life on them or not. Ironically, it was the scientist who argued they do on the principle that God wouldn't have wasted the planets by not putting life on them, whereas the theologian argued that the planets are mostly not habitable based on physics. And Whewell, the theologian, was instrumental in moving us to accept the fact that they're mostly not habitable. So our concept of a planet changed. They're not all exactly like the Earth. They don't have life, but they're like the Earth in substantial ways geologically. Then we started discovering smaller and smaller asteroids. And very briefly, in the early 1800s, they debated whether they should be planets. And the astronomers decided almost unanimously, except for like one astronomer, they all decided, yes, they are definitely planets. We don't have any theory that would necessitate putting them into a different category. And so after that, for 150 years, all asteroids were accepted as planets. But as the asteroids got smaller and smaller and smaller, that got us further away from the concept of Galileo because they became less and less Earth-like and less geologically complex. Even in 1948, the International Astronomical Union wrote, in the case of a planet that passes closer to the Earth than the orbit of Mars, a definitive orbital parameter can be given after a single opposition, provided that the planet has been well observed. Talking about asteroids, calling them planets. Not minor planets, planets. The whole literature shows that they were considered planets all the way into the 1950s. But the public didn't go along with this. Okay, the public didn't even accept heliocentrism until 200 years after the scientists. The late 1700s, the early 1800s is when the public finally accepted heliocentrism. And when they did switch, science communication and education were so poor in that period that they did not accept the entire package. So they smuggled in elements of astrology and theological interpretations of planets in order to make the planets be about us, even though they don't orbit us. And so we've gone through, I don't have time to go through all of this, but how the concept of a planet evolved in the non-scientific literature. This is really interesting. These hybridized geo-heliocentrist concept of a planet. The sun's a planet, the moon's a planet, Mercury, Venus, and the Earth is a planet. They're all planets. Everything's a planet. The concept evolved, and by the mid-1800s, it settled on this idea that the sun is not a planet because it's a star. The moon is not a planet because you don't need moons in astrology. Moons are always with their primary, so it undermines astrology if we include them as planets. And the asteroids are not planets because you can't really you can't make a meaningful argument that they're orderly enough to communicate information to the Earth. And the theological argument was that the asteroids must be a destroyed planet because God wouldn't have made it messy. And since, therefore, it must be a planet that got destroyed after humans ate the apple in the Garden of Eden. And there's literally that in the literature. So we've traced how the concept of a planet evolved in professional, educational, cultural, and oral traditions. And we can see that scientists went to this Copernican concept of a planet, which is not based on orbits. The public resisted it. They created a folk taxonomy, which was more aligned with astrology. And then that crept, by the late 1800s, it crept into the educational literature, literature written by geographers and educators who are not astronomers. And then it wasn't until the 1920s to 1940s that the astronomical community stopped calling moons planets. And that happened in a period, this is the bibliometrics in astronomy and planets and satellites. And there was a period, we don't know why it happened, about 80 years or 70 years when the astronomical community stopped growing. Interest in planets, this is a log scale, this goes down 2/3. A 2/3 reduction in productivity studying satellites. It was during that period of neglect that astronomers stopped teaching Galileo's concept of a planet. And so the next generation of astronomers weren't corrected. They kept the cultural view that they learned in kindergarten, and that's how we got stuck with it. In the 1950s, that's when asteroids got reclassified as non-planets based on accretion theory. We now had a theory which made it meaningful to put them in a different category. Kuiper argued that the small non-rounded asteroids are not true planets, but the large rounded ones like Ceres are true planets. And within 10 years, astronomers stopped calling them stopped calling them planets. Okay, the presentism fallacy is a well-known fallacy among historians where you interpret past events as if they were motivated by modern beliefs that didn't exist back then. And you can see the presentism fallacy creeps into astronomy textbooks sometime after the 1950s, and people started saying, well, of course moons aren't planets, of course asteroids aren't planets, we know that. And so they reinterpreted this false story saying that it happened way, way back when really it didn't. Okay, so I'm going to skip over all of this. We've shown in the literature that planetary scientists still call moons planets. Hundreds of examples in the literature just after 2006. So rejecting the IAU, continuing to use the meaningful definition instead of the IAU definition. And we do this in the context of discussing complex geophysics. The Earth as a planet literature is all about complex geophysics, has nothing to do with Earth clearing its orbit. The geological complexity of planets is very diverse, but there's percolation of shared features across the whole set. If you pulled one ring, all the rings would come. The only one feature that they all have in common is they're all gravitationally rounded, because that's when all these different types of geological complexity seems to turn on in the physics. Okay, so we could use geological complexity as a way to define planets, because all the different size objects on a log scale, it's between gravitational rounding and nuclear fusion where complexity is maximized. But for now, we're saying gravitational rounding and nuclear fusion are proxies to roughly describe this region, and we think that is a meaningful concept to define what we're talking about in planets. Okay, I'll skip over this. This is the real history of how planets evolved. So, is Pluto a planet, and does it matter? Well, Pluto, ironically, is possibly the second most geologically complex planet in our solar system after the Earth. Some might say Mars, some might say Titan, but I think Pluto probably has more types of complexity than any of the other planets. So it's ironic that the most planety planet of all is the one that we're saying isn't a planet because it didn't clear its orbit. And does it matter? Yes, because concepts like planet are nouns, verbs are like are things that are actions like planet formation, origin of life, and we need nouns that go along with the verbs, align with each other so that we can describe scientific theories, and they evolve together. And taxonomy is part of the scientific process. It's theory laden, but it drives mental abduction of hypotheses, and it's important for the way that science operates. Okay, so that's the talk. I hope I've made my case. I think Pluto's a planet. You're free to disagree, but thank you. What's that? Okay.
Well, thank you, Dr. Metzger, for that wonderful talk. Does anyone have any questions? Sure.
Yeah, so if Jupiter has Trojan satellites or asteroids in its orbit, how is it considered clearing its orbit?
Yeah, so it's been pointed out, as you said, that, okay, so Jupiter has Trojan asteroids sharing its orbit. So how can Jupiter be said to have cleared its orbit? So that's another symptom of the problem with the IAU definition. There were several problems. First of all, we don't use it in science. Second of all, it's sloppy. They didn't say what they meant by clearing an orbit. And people that like the IAU definition always go, yeah, well, it's written really badly. We don't really mean that. What we really mean is gravitational dominance. And so you gotta, give it some slack. And then the third problem is it was written only for our solar system because they said, well, we don't know about other solar systems yet, and so we'll leave that for the future. Well, the verdict is coming in. The architectures of other solar systems are mostly not like our own, and we really think that the definition isn't good on that count as well. Thank you for the question. Question? Oh, yes.
And just to motivate the conversation, what if you put Earth where Pluto is? Would it have cleared its orbit?
That's a good question. I think the answer is no. I would have to go run the numbers to be sure, but I've heard Alan Stern say if you put Earth at the orbit of Pluto, it would not clear its orbit. Now, I've heard Mike Brown say, yeah, but Earth isn't at the orbit of Pluto. And that's important because the solar system is orderly, and that's part of the orderliness of it. But that's our whole point, is that we're not trying to communicate the solar system is orderly. That's what they used to believe under astrology, right? We're trying to communicate that it's dynamic and changing and even chaotic, and it's beautiful in its emergent complexity and dynamism. And so let's not keep focusing on the orderliness, which is incomplete, it's contingent on external exogenous events, and it's temporary. It's going to get disturbed eventually. When a star, maybe 5 billion years from now, when a star goes by our solar system, it's going to mess up all the orbits. Or when Andromeda comes and passes through the Milky Way, the Andromeda galaxy, it's going to mess up all the orbits. It's temporary. It's contingent because most solar systems aren't like ours with small terrestrial planets in such a wide band. So we don't think this, there's a perspective bias maybe it's important for the orderliness so that on our planet we could have life. So because we're on a life-supporting planet, there is a perspective bias and we're not seeing the way most planets really are. That's one possible answer. But anyways, I agree. I have done these numbers. I have run these numbers. If you put a planet exactly like the Earth in the habitable zone of a giant star, then it would not clear its orbit. But if you put a large asteroid in the habitable zone of a red dwarf star, it will clear its orbit. So there you go.
Thank you.
I think it's interesting that you called Pluto like the most planety planet because of all the planetary processes that happen on it. In that case, what do we think about like gas giants and stuff like that? Are they less planety, more planety, or are they just like less?
That's a good question. So if Pluto is the most planety planet because of all the different emergent examples of geology, then is Jupiter less of a planet because it's mostly gas? It doesn't have all of these same features. But so we would argue that Jupiter, I don't know, this is a notional graph. Jupiter might be down here somewhere. It's not the peak of complexity. The planet with the most complexity is a planet that has a civilization on it with computers and video games and all that. You know, that's extreme complexity. That doesn't happen on a star. It happens on planets. But so Jupiter, they don't all have to be as complex as each other. But Jupiter is a really complex planet. It's got geomagnetism. It's got all kinds of fluid flow physics. It's got chemistry in the physics. It's got layers. And down deep, we think it has a solid hydrogen ice solid core, hydrogen metal core. And we can't see all of the complexity because it's buried under this opaque atmosphere. There's probably a lot of other things that we don't even know about yet inside Jupiter. We think that a star is less complex than a planet because once nuclear fusion turns on, you get a huge outflux of energy. That energy tends to break valence shell bonds, breaks down the chemistry, and that huge flux of energy is a homogenizing effect, which reduces the complexity. Now, stars are still complex. You know, there's a lot of physics in a star, but we think it's less complex than most planets, and we think there's a qualitative difference. So this is, and by the way, this is a proposal. We have this idea of what we mean by planet, and we're trying to come up with a way to define it, because a planet, I mean, a definition is different than a concept. We have a concept of a planet. We're trying to create a definition that very briefly captures the concept. So defining is a different process than conceptualizing. Okay.
We have time for one more question. Anyone has one? All right. If not, let's thank Dr. Metzger.
Thank you.
All right. So with that, we're going to go ahead and take a 20-minute intermission. For anyone who wants to get food, drink from the bar, please tip your bartenders, everyone. They're doing a fantastic job for us, so please pay it back for them. And yeah, in the meantime, we will also have some space trivia for everyone. So let me see if I can set that up as well.
Do we? I can quit. I can cancel the recording. They are, but I can close it if you want.
Do you want to? We can go ahead and stop it right now.
Kevin needs a chair.
Huh?
Kevin needs a chair.